Imagine trying to teach AI, artificial intelligence, to solve these incredibly abstract, really complex mathematical proofs. We're talking the kind of thing you see at the International Mathematical Olympiad, the IMO, that challenge even, human geniuses. For you listening in, we want to cut through some of the hype and show you how AI is actually tackling some of the hardest problems out there. Think of this as a shortcut. Yeah, a shortcut to getting up to speed on this frontier. So our focus today is this groundbreaking new development from ByteDance Seed AI for Math. They've got these two systems, Seed Prover and Seed Geometry. I was going to dive deep into their latest research paper. It really details how these AI models are pushing the boundaries of automated mathematical reasoning. Our mission really for this deep dive is to unpack the specific things, the innovations that led to their amazing performance. We're talking gold medal level results at the IMO 2025. We'll look at their unique takes on formal verification, refinement, and just how they strategically solve problems.
Yeah, it's fascinating because when you think about it, AI has historically had this major roadblock with sophisticated math reasoning. I mean, large language models, LLMs, they're great with natural language, right? Impressive stuff. But theorem proving, that's been a real struggle. And the core issue, it really boils down to not having clear supervision signals. Like, how do you automatically check if each step in a proof written in plain English is actually logically correct? It's incredibly tough.
Right. I mean, try to picture grading a math test where everyone just scribbles their thoughts down, no clear steps, no standard symbols. Yeah. It'd be a total nightmare for anyone, human or AI. That's kind of what natural language proofs are like for an AI. But this is where formal languages like Lean apparently just changed the whole game.
That feedback loop from Lean, yeah, it's absolutely the game changer. It's so powerful because these formal languages, they don't just give you a precise path. They have this like built-in verification system. So unlike natural language, Lean gives an instant, clear signal. Is this step right or wrong? It's like a verifiable truth check. And that is absolutely crucial for training AI. It makes reinforcement learning super effective. The system knows immediately if a step works or not, so it learns and adapts way faster. We saw glimpses of this before. AlphaProof used Lean, managed to solve 3 IMO problems. That was a big deal then.
Okay, so if that's the foundation, how do LLMs actually do the formal proving? A paper mentions 2 main ways, right?
Yeah, broadly speaking, you've got step-level provers. They generate the Lean code line by line, which is good for interaction, allows for tight feedback, but maybe too granular, too slow for really complex proofs.
And the other way?
The other way is whole proof generation provers. These try to generate the entire proof in one go. Historically, though, they didn't have much interaction. But the recent trend, and this is important, is combining these whole proof models with long chain of thought reasoning. And this kind of hybrid approach, it performs substantially better. It really sets the stage for what Seed Prover does.
Okay. So Seed Prover builds on that. Let's really get into Seed Prover itself then, because it sounds like the real engine behind these big math breakthroughs. It's a whole proof model, you said, but with some unique twists.
Exactly. Critical distinctions. Probably the most significant one is its use of lemma-style proving. So instead of trying to generate one massive proof from start to finish, Seed Prover first generates useful intermediate lemmas. Think of them as smaller, self-contained subproofs. Mini proofs that help solve the bigger problem.
It sounds more like how a human mathematician might work, right? Breaking down a huge problem into smaller, manageable steps. Seed Prover does that with these lemmas.
Precisely.
Yeah.
And you have to ask, why is breaking it down like that so powerful for an AI? Well, first, lemmas give you clear progress markers. The system knows, okay, this subproblem is solved, this one still needs work. Second, they're modular. You can compile them, store them separately. They become like reusable building blocks of knowledge. And maybe the coolest part, proved lemmas go into this lemma pool. It's a shared resource. They could be used later in the same proof or even help solve other problems down the line. They can even inspire new approaches.
Wow, okay. And building on that idea of breaking things down, there's this other innovation. Conjecture proposing. This sounds really interesting.
It is. So Seed Prover is trained to suggest potentially useful properties about the problem. Uses chain of thought reasoning to do this, but crucially doesn't commit to one direct solution path right away. It's more about broad creative exploration first.
So like brainstorming. Instead of just charging ahead, trying to solve it directly, it first throws out a bunch of ideas about the problem itself, like, is this function injective? Is it periodic? Is this number special somehow? That kind of thing.
Exactly that. It's a big shift from approaches that just assume you can find the solution directly. This lets the model stumble upon useful properties, things it might totally miss if it only focused on a direct line of reasoning.
Hmm.
And it doesn't just propose one or two ideas. It generates like 10 to 50 candidate conjectures for each problem, all in parallel. Really boosts the diversity of ideas.
And driving all this clever reasoning, there's the adaptive training strategy. You mentioned it uses reinforcement learning based on something called VAPO.
Yes, it's a multi-stage, multitask RL strategy. And the training itself is, well, incredibly sophisticated. It's not just fed formal statements like older systems. SeedProver gets a really diverse mix of prompts. Formal statements, sure, but also natural language hints, natural language proofs, lemmas from its own past attempts, both successful and failed ones, and critically, that direct feedback from the Lean compiler. This constant feedback loop plus the diverse input, it makes the model really adaptable, really robust during the actual problem solving, the inference stage.
That adaptability sounds absolutely key, especially for tackling problems of different difficulties. And this comes out in their 3-tiered test time scaling, right? Their thinking budgets.
Exactly. It's how SeedProver adjusts its computational effort based on how hard the problem seems and how much time it has. So let's do both deep dives and broad searches.
So what's the first tier, the light inference setting?
In the light setting, it iteratively refines its proofs. It'll make maybe 8 to 16 passes, constantly using that Lean compiler feedback and also summarizing its own progress to improve the next attempt. And this iterative process, it can achieve way more than just a single shot. Like it solved IMO 2022 problem 2, a pretty tough geometry one, in just 1 or 2 hours without refinement. They estimated it would need over 8,000 attempts.
Wow. So it's really learning as it goes, not just brute forcing. What kind of improvements did they actually see it making during that light refinement?
Well, 2 main things. First, the obvious one, fixing syntax errors the Lean compiler flagged, essential for formal proofs, of course. But second, and more profoundly, it would refine its initial proof ideas. Sometimes it would completely change tack, altering the whole reasoning path to find something more elegant or, actually correct.
Okay, then for the harder problems, you move up to the medium inference setting. How does that scale things up?
Right, the medium setting adds another layer. You still have the outer refinement, like in the light setting, working on the main problem. But if that outer process generates a lemma that's proving difficult, it spins up an inner refinement process just for that tricky lemma. And if that inner process manages to prove the lemma, boom, that success gets fed straight back, updating the prompt for the outer refinement. So the system learns from its intermediate successes. This approach cracks some really tough nuts. IMO 2003 problem 6, IMO 2020 problem 5, and even IMO 2025 problem 5. The final proofs could get huge, like over 1,000 lines of Lean code.
Okay, and then the final level, the heavy inference setting. This is for the absolute monsters. The biggest challenges sounds like maximum effort.
Maximum exploration, yeah. It starts totally fresh with an empty lemma pool. And then it just goes wide, generating thousands of conjectures. Like the default is up to 5,000 potential ideas.
Yeah.
Then it uses the life setting to basically try and prove or disprove every single one of those conjectures. Yes.
If
one gets proved, it gets added to this growing lemma pool, and it doesn't stop there. It even proposes more conjectures based on the lemmas it just managed to prove. It's constantly building its knowledge.
So it's like it's building its own personalized dynamic library of mathematical facts as it works, getting smarter with every sub-problem it solves.
That's a really good way to put it, yeah. So after maybe days of this thinking, this lemma pool might have several thousand non-trivial mathematical facts. Then it scores all these lemmas. Scoring is based on proof rate, interestingly. Lemmas that were hard to prove with a low proof rate often turn out to be critical for the final breakthrough. Also semantic relevance and length. Then it picks, say, hundreds of the top-ranked lemmas and uses those, along with the medium setting, to finally tackle the main proof. This super intensive multi-stage process is what let it solve IMO 2017 P2 and IMO 2025 P3 and P4.
It's incredible. SeedProver is clearly a massive step forward for abstract math proofs. But geometry often needs a different approach, doesn't it? That's where C-geometry comes in, because Lean itself had a gap there.
That's exactly right. Formal systems like Lean, powerful as they are, weren't really built with complex geometric reasoning, deep in their core. So C-geometry was created to fill that gap. It builds on earlier work, like tongue geometry. It cleverly combines trained neural models, which are great at predicting those extra lines or points you often need to add in a geometry proof, the auxiliary constructions, with specialized symbolic reasoning engines. These engines do what's called forward chaining derivation to actually complete the logical steps of the proof. It's a neurosymbolic approach blending neural net intuition with symbolic logic precision.
Neurosymbolic.
Yeah.
Okay. And that forward chaining part means?
Forward chaining just means it starts with what it knows the initial facts of the problem, and then logically deduces new facts, step by step, building outwards until it reaches the final conclusion, the thing it needs to prove.
Got it. And one of its key innovations seems to be its extended domain-specific language. So instead of telling it every single tiny step with a ruler and compass, draw this line, find point A, draw that circle, it can use shortcuts. Like just saying, construct the isogonal conjugate or find the x-similitude center. That sounds way more efficient.
It is massively so. The simplification is critical. While it's all ultimately grounded in basic ruler and compass steps, C geometry groups common, often complex sequences of actions into these single composite actions. It makes the way it represents geometry constructions much, much shorter, more concise, and that dramatically cuts down the computational load, both for the neural model suggesting the steps and the symbolic engine verifying them.
And efficiency seems to be a theme because another huge innovation is the extremely fast reasoning engine. They rewrote the backend from Python to C++ Day.
Yeah, and the result was 100-fold speed increase.
100 times. That's not just a small tweak. That's like going from a bicycle to a sports car for every calculation. That must fundamentally change what it can explore, right? Yeah. The scale.
Oh, absolutely. That speed isn't just flashy, it's foundational. Those forward-chaining engines, they naturally slow down the deeper the search goes, so boosting efficiency by 100x. It allows for vastly wider and deeper exploration of all the possible geometric steps. Plus, the C++ implementation is just much better at managing memory, which also helps tackle larger, more complex problems.
They also use a top-tier, exceptional large language model, part of their seed family, trained on tons of coding and math data.
Yes, a very powerful LLM. And what was interesting, maybe surprising, is that unlike some previous approaches, they found a single policy model was enough. That simplified the whole training and solving pipeline quite a bit. This LLM is really the core brain, suggesting the constructions and steps.
But all this power gets put to work through extensive search capabilities.
Right. It uses something called beam search, but in a distributed way. Imagine you have a team searching for something. Instead of just one person following one path, beam search keeps track of several promising paths simultaneously. And C geometry does this across multiple processors, with different parts communicating and sharing progress. GPU processes talk to each other. CPU threads handle reasoning steps asynchronously. They manage to overlap the reasoning cost with the LLM's thinking time, making the whole thing super efficient and scalable. Lets it search that geometry space incredibly quickly and deeply.
Okay, so we've got Seed Prover for abstract math, Seed Geometry for the visual stuff, all these incredible innovations. How did it actually perform on the biggest stage, the IMO 2025?
Right, ByteDance was officially invited. And the results were, frankly, astounding. Seed Geometry basically insta-solved problem 2. Just bang, done. Seed Prover then proved problem 5 using its medium setting. And for problems 1, 3, and 4, it needed the heavy setting, that really deep exploration. Now, problem 1 technically was finished just after the official deadline. But still, the overall score, 5 out of 6 problems fully proven. That's solidly in the gold medal territory for a human team. Just remarkable performance.
Wow. And it wasn't just a fluke at the IMO, right? You mentioned these systems are crushing benchmarks elsewhere, too. How does C geometry compare to, say, alpha geometry?
Yeah, it's not just competing, it's leading. C geometry actually outperformed alpha geometry 2 on past IMO geometry problems. It solved 43 compared to 42 for alpha geometry 2.
Yeah.
And on the harder IMO shortlist problems, C geometry set a new state of the art. 22 solves versus 19 for alpha geometry 2. So yeah, it's consistently better. Even on the really tough geometric challenges, it's basically the new benchmark in AI geometry proving.
And Seed Prover, beyond the IMO problems.
Seed Prover is showing really broad strength. It got that 78.1% success rate across 155 past IMO problems, which is impressive in itself. It nearly perfected Mini2F 99.6%, which is a core benchmark for formal math. On Putnam Bench, that's university-level competition problems, notoriously tricky, made a huge jump. Solved 331 problems where the previous base was 86. That shows real intellectual horsepower. It even made progress in combinatorics, which is known to be hard for these systems, getting 30% on CombiBench. And it did really well on complex real-world formalization tasks in Mini-CTX-V2, hitting 81.8%. So connecting this to the bigger picture, what we're seeing is a consistent, really robust capability across a whole range of mathematical fields, from competition math to these complex formalization projects. Though it's worth pointing out combinatorics is still comparatively harder for it. Those problems will often need different kinds of creative leaps, perhaps. Okay, so this is incredibly impressive from a research perspective, but why should you, our listener, really care about AI solving math Olympiad problems? What's the bigger meaning here beyond the scores? Well, it's about much more than contest results, absolutely. What this really signifies is that we're developing AI systems that can not only solve incredibly complex problems, but verify their solutions with absolute mathematical certainty. Unshakable proof. Think about the implications of that. Ensuring critical software, like in self-driving cars, medical equipment, financial trading systems, is provably free of bugs. Imagine rapidly validating complex scientific theories in physics or biology. These formal languages, like Lean, allow for quick proof verification. It's way cheaper than teams of human experts checking things and far more reliable than, say, previous AI attempts using just natural language understanding. It genuinely opens up possibilities for a new kind of human-AI collaboration in fundamental science and engineering.
It really does shift the landscape. And you mentioned something earlier, looking that helped make all this possible behind the scenes.
Ah, yes, looking. It's essentially a user-friendly Python interface for Lean that ByteDance developed internally. It sounds simple, but it was crucial. It makes interacting with Lean much easier and more scalable. To do the kind of massive model development and inference they did, they needed this. It handles things like stateless design, version control, memory tracking, simplifying proofs automatically, handling many interactions at once, all vital for running experiments on this scale.
Right, the infrastructure needed to support this level of research is often overlooked, but totally essential. Okay, so let's just recap quickly. We've really unpacked the incredible progress made by seed prover and seed geometry in automated math reasoning. These systems use formal verification, this cool lemma-style proving, really clever multi-tiered thinking strategies, powerful geometry engines, all coming together to get state-of-the-art results, including proving 5 out of 6 problems at the IMO 2025. A huge leap. But here's the really mind-bending part, the provocative thought from the paper itself. They say future work isn't just about solving problems we already know how to solve, even if they're hard. They want to combine these formal systems with LLMs to go after open conjectures, problems that have stumped human mathematicians for decades, maybe centuries, unsolved mysteries. Imagine that. An AI not just confirming what we know, but actively helping us discover entirely new mathematical truth, pushing the frontier of human knowledge itself. So thinking about that, what unsolved mystery do you think AI might tackle next? What's the next frontier?